So let's start talking about architectures. And so far, we've seen this concept of building blocks. So by now, you should be familiar with the convolution operation, the nonlinear activations, and the pooling. And I kept on mentioning how this was a sort of building block. And you can very much think of these as Lego pieces. And there are many different ways. If you have lots of Lego pieces in front of you, there's almost, as long as you have Lego pieces, you could keep on chaining them together and come up with more and more intricate ideas for your architectures. And that's essentially what happens in the world of CNNs. We have these basic building blocks, and people have been experimenting with them over the past few years and decades to figure out which architectures work best. So this is what we're going to review today. But first of all, how do we know which model is better? What does it mean for a model to be better? And I put it in quotation marks on purpose, because better might be different based on the applications that you're using. Does better mean more accurate? Does better mean more lightweight? Does it mean that it's faster? Does it mean that it's more generic, that you can adapt it to different tasks easier? There's obviously, the answer can't be yes to all of these, it can't be no to all of these. It depends on your specific use case. And typically we try to find the best trade-off between these categories. So here we're going to go over some of these models that are presented here, but you have, for example, the different accuracies for models and the amounts of parameters. So here you might decide, well, is accuracy more important or is size more important? And you can compare the different accuracies. And of course, if you could get similar accuracies for a smaller size, then typically that's the kind of network you might decide to be better for your use case. So how do we compare models? Luckily, in the deep learning community, a lot of data is open source. So it's somewhat easy to compare models between one and the next. It's very easy for me to claim that I have a better model, but for me to demonstrate that I have a better model, all I have to do is take a data set that everyone else is trained on, train my model on it, and demonstrate that my model performs better than other models. And this, again, this better can be defined by some kind of metric. So it's very common in the deep learning literature that you read a paper and you first thing you might try to do is look for this kind of table. You have a table and it presents the model being presented, the other models in literature, some kind of metric, and then they highlight this metric in bold. And usually the higher is better kind of metric approach, and they say, well, our model is better because compared to every other model, here is how we scored on this specific task. And when you're able to show this, usually you win either a competition or you win a publication, and everyone starts using your model. So this is generally how we benchmark models in the deep learning community. We compare on data sets that are publicly available, and we try to reproduce these results and other people's results and demonstrate that our models perform better than other people's models.